Okay, so this is a fun one. And a little weird, so bear with me a little bit here. We've got this thing rolling. So let me make a coordinate system like this, so we can talk about what's going on. I still draw a free body diagram. I've got a normal force like that. I've got a weight mg, and if I assume that I start right at the unstretched length of the spring, then as soon as I start pulling to the right, it's going to give me a spring force that looks like this. And then I'm going to have a force P pulling up like this. Now, the trick here, and where this one can get a little confusing, is this force is constant. And the spring force is equal to K times delta X, right? And what's important there is that initially that constant force is going to overpower the spring force. And what's going to happen is that this cart is going to accelerate. So when this thing, and the question asks for what is kind of what's the maximum stretch that the spring is going to experience, and that's going to go past the equilibrium position, because this thing is going to be moving pretty fast, and the spring is not only going to have to balance out the force P, but it's going to have to slow the cart down. So that's the key concept here. So this problem, if you're okay with that, then this problem is actually not too bad, because we're just going to use work energy principle. And when we do that, we know that the work from state 1 to state 2 is equal to the change in kinetic energy. So when this spring reaches its maximum stretch, then the velocity reaches 0, and then it's going to start going backwards. Eventually it'll end up in an equilibrium position where the forces just kind of balance out. But initially, as you shoot past that point, it'll have to bring it back, and as it starts back, the speed will be 0. So it starts at rest, it ends at rest. That's going to be 0. That's kind of neat. Initially it makes you think it's going to be super easy, but it's still not easy. So the work done by the spring, so if it's moving up and to the right, spring is pulling back and down, that's going to be minus 1/2 K delta X squared. The force P is going to pull over that whole distance. It just lines up, so it's doing positive work. And then the component of the gravitational force that is kind of in this direction, let's see if this helps, right? So there's theta, and the gravitational force is going down like this. So there's theta, right? There's 90 minus theta, and there's theta again. So that means that the component in the negative x direction there is mg sine theta. So that's going to be minus mg sine theta times delta x equals 0. And what's interesting about this one is mg cosine theta, the other component of the gravitational force, doesn't do any work because it's always perpendicular to the motion. So for something like this, we can divide out the delta x. We're assuming that's going to be positive, some positive number, right? So we're going to have P minus mg sine theta minus 1/2 K delta x equals 0. And so if I bring the K delta x over, so then I'm looking for delta x is going to be equal to 2 over K times P minus mg sine theta. So that's pretty nice. It's not the same as the equilibrium position, because as you start pulling up, that force P is constant, and it starts out much bigger than the spring force. And so as it pulls, you're going to turn a lot of the work into kinetic energy, and so that card is going to zoom past the equilibrium position, and the spring is going to have to overcome not only the force P, but it's going to have to take care of the energy as well. It's going to have to absorb some of that energy. So this is great. Nice job.